My talk tonight is about the deep history of the Blue Ridge and the Valley, a topic that's near and dear to me and is instrumental in understanding the geology of Shenandoah National Park and the Blue Ridge Parkway and the whole Shenandoah Valley and the Waynesboro area. By deep history, what do I mean? I mean history that starts, we're going to go back about 600 million years to talk about some of the older rocks in the area, and we're going to continue to talk about the history up until about 100,000 years ago. So by deep history, I'm talking about geologic history and history of the landscape formation. This is all history before any human beings lived anywhere in the state of Virginia. So that's what I mean by deep history. All right, so here's a synopsis of the geologic history. I'm looking for the point. What happened to the pointer? Well, I guess I don't have a pointer today. I'll just point with my finger. All right, so the first thing we're going to be talking about is the Precambrian. About 600 million years ago, there was we had the beginning of the inception of an ocean, not the Atlantic Ocean, but the Proto-Atlantic Ocean, and I'm going to be talking about that. And there was a major volcanic episode associated with it. This led to the formation of the Paleozoic seas between 500 and 350 million years ago. These included a lot of limestone. There's lots of fossils involved with this. Then about 250 million years ago, the Proto-Atlantic Ocean closed. There was a collision between North America and Africa, and the Appalachian Mountains formed. And that, of course, is a big part of what's going on in Virginia. And then, obviously, since we're no longer attached to Africa, we're separated by the Atlantic Ocean, we have the big split, which began about 230 million years ago and which continues even today as the Atlantic Ocean gets wider and wider. And then finally, I'm going to talk about the evolution of the modern landscape and how geologic history all ties into that, and the various landform processes that have led to the present-day shape of the Shenandoah Valley. All right, Precambrian volcanoes of the Blue Ridge. Now, if you go up in the Blue Ridge Parkway, or if you go up into Shenandoah National Park, one of the rocks that you're going to see a lot of is what's called the Catoctin Greenstone. Now, on some trails of Shenandoah National Park, you actually see things like this. These are basalt lava flows, and as they cool, they form these what are called basalt columns. Even though these rocks are almost 600 million years old, you can still see these columns. You find these in much younger volcanics as well, but these are 600 million years old. All right, now why do we call it the greenstone? Well, if it's a volcanic rock, why don't we just call it a volcanic rock? Well, geologists are very straightforward people, and this particular volcanic rock has been subject to the action of very hot, salty water, what we call hydrothermal alteration. And it has turned the original minerals of the rock into a bunch of these green minerals. So we have this sort of pea green stuff, which is epidote, and this darker green stuff, which is chlorite. And these are all minerals that have formed in the process of hydrothermal alteration. And if you see these rocks in the Parkway or in Shenandoah National Park, you'll see this green color. It's very characteristic of the Catoctin Greenstone. And as I said, these are the volcanics that heralded the formation of the Proto-Atlantic Ocean, also called the Iapetus Ocean, Iapetus being the father of Atlas. All right, Paleozoic seas. So once this ocean started going, most of Virginia was then underwater. Initially, as the land eroded into the new ocean, there was lots of sediment that was washing off the land, forming sandstones and shales. But then as the ocean got wider, the seas became quieter, warm tropical seas. We had these limestone seas, these subtropical seas, similar to what we might see today in the Bahamas, covering much of Virginia. All right, so this is some of the sandstone. This is the Chilhowie sandstone. It's a very early Cambrian sandstone. We really don't know exactly what its age is because the only fossils that we find in it are these guys. And these are what are called trace fossils. They're known as Scolithus tubes. We don't know what animal made them, but they're very common. They're very abundant. And if you find examples of the Chilhowie sandstone in your travels in the Parkway or in the valley, you'll very often see these streaks running through there, which are these tubes left behind by these animals. Now, if you're very lucky and go on a really good field trip, perhaps, you might be able to find fancier-looking fossils, such as this Trilobite. It's a distant relative of modern insects and modern crabs and what have you. But these are all extinct and have been extinct now for 300 million years almost. But this is something that crawled around in these Paleozoic seas. However, most of the valley is underlain by a rock type known as limestone. This is a quarry near Stanton in limestone. Limestone is a rock made of calcium carbonate. And this quarry here, they're mining it mostly for cement because they use limestone in the formation of cement. They also use it, incidentally, as a mild abrasive in toothpaste. And if you've ever had a tummy ache and taken some Tums, what you're doing is chewing on a piece of limestone. It gets down to your stomach, reacts with the acid, and neutralizes it. And that's going to be an important concept a little later on because limestone is very slightly soluble in acidic solutions. And so that's going to be important, so keep that in mind. Now what we find nice fossils in this. This is a fossil of an animal known as a brachiopod. It looks a lot like a clam, but you know, clams are not symmetrical. Brachiopods are symmetrical, and they're actually not particularly closely related to clams. In fact, there are two main branches of multicellular life, and clams are on one branch, and brachiopods are on another one, and we're on the same branch as brachiopods. So in a sense, we're more closely related to these guys than clams are, although to say it's a close relationship would be certainly stretching it. Also a lot of ancient corals. There's a lot of coral reefs, ancient coral reefs in the Shenandoah Valley. This is an ancient coral called Favosites. It's now extinct, of course. And of course, it can make very nice little jewelry here if you want to polish it up. My favorite fossil, my personal favorite fossil from the limestone seas is a stromatolite. This was collected in a quarry in Bedford County, Virginia. It weighs about 2.5 tons. It's a fossil dome built up by millions and millions of tiny little algae over probably hundreds, maybe even thousands of years. And to my knowledge, this is the largest intact stromatolite ever recovered. And it is on exhibit at the Virginia Museum of Natural History. All right, the big crunch. Well, after 250 million years of relative quiet, the African and North American continents collided about 250 million years ago. The collision resulted in the formation of the supercontinent Pangaea, and the Appalachian Mountains were formed. And what happened was all of the rocks, all the sedimentary rocks, including the limestones, were all folded. They were squished together and folded like the folds in a rug if you pushed along the surface of a floor. And the rocks of the Blue Ridge were thrust westward about 100 kilometers from their present position, just pushed up over everything else 100 kilometers to the west. And so this Blue Ridge is not the modern topographic Blue Ridge, which I'm going to talk about the formation of this in a minute. So here's the collision. Here's a before and after picture. You can see the Iapetus Ocean here. The limestone seas are generating in here. And then after the collision, you can see Africa and North America have smashed together. What I like to tell people is the closest beach to Virginia at this point was probably in the southwestern United States, maybe New Mexico or Arizona. And so this is how the Appalachian Mountains formed. And this is very important because the structures that formed during the Appalachian Mountains really dictate a lot of the topography that we see in the valley and ridge today. Were the Appalachians as high as the Himalayas? This is probably the most popular question I get. We don't really know. They may have been, but it's very difficult to gauge that because they've been eroded. They've been eroding for a quarter of a billion years, and so it's hard to tell how high they were originally. So here's the collision, sort of a cross-section of it. Here's the Blue Ridge. This is a bunch of very complicated rocks that came from the edge of the continent. They're mostly igneous and metamorphic rocks, and they were just pushed westward bodily by the force of this collision. The rocks here, the sedimentary rocks of the Shenandoah Valley of the limestone seas, were then squished and folded by this westward push. If you go to Iron Gate near Clifton Forge, you can actually see one of these folds, and here it is right here. It's visible from the road, and you can see that this push westward through all of these rocks, these layered rocks, into this series of loops and folds. This is a schematic diagram, but you can see it if you just look at the topography even. You can see how these rocks have these loopy, kind of folded, funny-looking shapes. These are all folded sedimentary rocks. By about 200 35 million years ago, Pangaea began to break apart. Obviously, we're no longer sitting next to Africa. The beach is now in Virginia Beach and not in Arizona. And the Atlantic Ocean began to form. And it's been getting wider ever since at about the rate your fingernails grow. So here we are. Here's the early Atlantic Ocean. There's the remnants of the Appalachian Mountains. There's Africa. And now the continents are slowly drifting apart as the Atlantic Ocean forms. Now, in Virginia, although they're not easy to find in the valley and ridge, we have evidence of this collision, and it's the same kind of rock that we find in the Catoctin Greenstone. This is the Catoctin Greenstone. Well, this is a diabase sill 300 million years younger than the Catoctin Greenstone, maybe closer to 400 million years younger. But it's the same composition rock, and it formed in the same geological setting. This formed when the Iapetus Ocean was tearing the continent apart. This formed when the Atlantic Ocean was tearing the continent apart. And we have these large horizontal intrusions of this rock and these vertical intrusions. And there's also volcanic rocks associated with the formation of the Atlantic that we find throughout Virginia, mostly on the to the east of the Blue Ridge, however. All right, now I'm going to spend the rest of this talk talking about the landscape today. Because it really is what we deal with on a day-to-day basis. It preserves a lot of elements of the geologic past, and it reflects the underlying rock. And the landscape has evolved and continues to evolve by a series of fairly well-understood processes that have actually led to how the valley and the ridge, the Blue Ridge and the Shenandoah Valley, relate to one another. All right. So first of all, I want to point out this is a geologic map. This is Massanutten Mountain right here. Here's Massanutten Mountain right here. So sedimentary rocks are composed of different layers that have different strengths. If you think, for example, of a pile of material, some of it is sand, some of it is clay, some of it is some kind of mush, and if you wash it with water, it's going to erode differently. Some parts are going to erode faster than others, and when you do that, the parts that erode most slowly are going to stand up as ridges. And so Massanutten Mountain actually has a ridge here, and this rock, it goes underneath and comes out on the other side, and there's another ridge here. It's a canoe-shaped fold in the middle of the Shenandoah Valley. All right? And so what we find is the sedimentary rocks that were formed in the limestone seas are folded like this, and the folding shows up very well on topographic maps, geologic maps. In fact, you can even see it on road maps. All right? Now, here's the Blue Ridge. Also a high stand, but you'll notice it doesn't have those same well-defined features. And the reason for that is that the Blue Ridge is igneous and metamorphic rocks. There's not a lot of contrast in how they erode, and so they erode pretty uniformly, and you get this single high ridge. Now the landscape, particularly in the valley, reflects the underlying rock type, and you can see this very well, particularly in the Shenandoah Valley. I think Joe mentioned karst before. Well, this is some karst topography. This is limestone bedrock, and as I said, limestone is very slightly soluble in acids, including acidic rainwater. And so what you have are these pits or sinkholes scattered throughout the entire landscape where a crack perhaps has been widened as rainwater comes down into it and slowly starts to dissolve in. And then finally, these things may lead into caves. And so many of you have probably visited some of these caves, these limestone caves, the Ray Caverns, Shenandoah Caverns, that are fairly common in the Shenandoah Valley area. And these are all in limestone, and these all formed by the dissolution via rainwater of the limestone. And these stalagmites and stalactites are actually formed when rainwater drips down, evaporates, and slowly deposits over thousands and thousands of years these beautiful cave formations. Now, of course, the high ground, and if we get west of the Shenandoah Valley, we're all of a sudden in an area of these ridges and valleys. And you'll notice there's a big difference, even in this aerial photo. Shenandoah Valley here, patchwork, mostly farmland, lots of cleared land. You get up into these ridges, they're all forested. They're no good for farming. They're very steep slopes. They're very poor sandstone soils. And so wherever there's limestone, you have this kind of flat topography that's very suitable for habitation and agriculture. But then any place the sandstone comes to the surface, here and here and there, and you can see the little folds in here. You can even see the county line here is following this fold right there. So when you have these sandstone ridges popping up at the surface, you form these steep ridges, and the little valleys in between are still limestone. And so there's agriculture in these little valleys that are cleared off, but you can really pick this up just looking at an air photo. So a big flat area, that's the Shenandoah Valley, and then this area over here where you've got the valleys and ridges. And there's a reason that the Shenandoah Valley is such a big valley in the valley and ridge. All right, just to refrain, here's the valley, relatively flat all across. There's Massanutten Mountain, which is a little fold in the middle of the valley. It's a reprise of the rocks that are over here. And in fact, this is actually sitting up on top of the limestones of the Shenandoah Valley. It's a kind of a remnant. And then again, here's the Blue Ridge, also folded, by the way, but because the rock types don't have any differential strength characteristics, it forms this nice, even, well, relatively even, but certainly not a clearly defined layered structure. All right, just a little aside here. Many of you have probably noticed as you've been driving down Route 81 or many of the roads around here, these funny patches on the sides of the mountains. These are scree slopes, and here's a close-up of one. And these things form when they're formed by weathering of hard, very nutrient-poor sandstone, specifically the Chilhowie sandstone. And these things are prehistoric. We don't know how long they've been there, but we do know they've been there long enough for a species of salamander that's endemic to these scree slopes alone to live here. So these things have been around for hundreds of thousands of years. People tend to think they're man-made features, but they're not. They're actually natural erosion features related to this kind of brittle, very nutrient-poor, hard sandstone that really doesn't let you develop much of a soil profile on it, and so you get these unstable slopes where nothing grows. All right, now we're going to talk about a little bit of landscape hydrology. All right, how rivers and streams have really shaped the valley and ridge as we know it today. Stream capture is a very important concept in this. Stream capture in the Blue Ridge. First of all, there's a fundamental difference between the Blue Ridge north of Roanoke and the Blue Ridge south of Roanoke. In the south, the Blue Ridge is a major drainage divide. It separates rivers that flow ultimately into the Mississippi and the Gulf of Mexico from rivers that flow into the Atlantic Ocean. So, for example, the James River, the Shenandoah River, the Potomac River all drain into the Atlantic. The New River, however, drains into the Ohio and ultimately the Gulf of Mexico. And so the New River is on the other side of this drainage divide. In the north, the Blue Ridge, although it's a really nice-looking ridge, is really only a local divide within the Atlantic drainage. It's a remnant, if you will, a remnant drainage divide. So here we, excuse me, here we can see this a little graphically. Here are all the Atlantic drainages going off this way. Here are the Mississippi drainages, mostly going into the Ohio River, sometimes via the Tennessee, sometimes via the New. And you can see, on this topographic map of Virginia, you can really see the difference between the Blue Ridge. Here it is in the north, where it's a single, undivided ridge. You get south, and all of a sudden, it's no longer a ridge, it's a plateau. So if I'm driving from Martinsville, for example, we go up the edge of this plateau, and we're up to Meadows of Dan, which is a flattish area. Most of this land up here is over 2,000 feet. So it's much higher than all but the highest parts of the Blue Ridge proper, all right, the northern Blue Ridge. So it's very high ground up here, and the drainages are all going off away from the Atlantic Ocean. So this is a diagram of what's called stream capture, and this is instrumental in understanding what's happening in the valley and ridge and in Virginia in general. All right, here's we can think of it this way. Here's an ancestral stream. We could call this the New River if you want, and this maybe is the Roanoke River. All right, the New River is at probably 2,000 feet, flowing through a a valley that's almost 2,000 feet high. The stream level here is almost 2,000 feet, whereas the Roanoke River down here is probably only 600 feet above sea level. So there's a 1,400-foot difference. And so when water flows downhill very fast, it cuts very fast. And so here we have the Roanoke River cutting back into this drainage divide, very quickly eroding it. And ultimately, it's going to break through. And when it does, it gets into the stream valley, it's going to divert this stream. Why is it going to divert it? Because the gradient here is so much steeper. So here it's a relatively low gradient, and this is like opening up a dam and letting it flow out. And so now we have this captured stream flowing into this drainage. And what's going to happen behind here? Well, that's a good question. Because the erosion now is so much faster, what's going to happen is this is going to erode out very quickly back in here. All right, and what you're going to end up with is a valley back in here and a remnant drainage divide up here. So this old drainage divide will now become just a ridge within this drainage system. And you can see this because within this ridge, you'll have these water gaps, areas where the stream captured and brought the stream from one drainage divide to another. And if you look at the Blue Ridge, you can see these in several places. Here's the water gap associated with the James River. Here's the Blue Ridge. Lynchburg's in this area. And here we have the James River cutting across the Blue Ridge. And the reason it cut across it is because here's a stream probably originally flowing to the north, and it got captured by the James and diverted, and now is flowing into the James River drainage. Here's some more water gaps associated with the Potomac River and the Shenandoah River. And you can see these highlands on both sides of the river here, where the river is cut across, and actually what it reflects is the river cutting across back into an old, much more high elevation river drainage. So again, we have a short stream with a very steep gradient and a long stream with a very low gradient at a higher elevation. When this gets over to there, it diverts it and it comes back and starts going down in there, and there's a lot of erosion going on now behind that old drainage divide. And you can see that here. All right, if you look at the plateau here, it's all high elevation. All right, and you can see that the elevation here is similar to the elevation in the Blue Ridge itself. All right, but the valley, the Shenandoah Valley, is at much lower elevation. And that's because once these streams started going to the Atlantic Ocean, it was a much shorter path. They were much steeper. They were able to cut down very quickly, and they were able to flatten out this valley, if you will. And so now we have this big flattish area with this old drainage divide separating it out. And you can see it happening also in the area where the James River is, in the area where the Roanoke River is. But in the areas where they haven't breached yet, this is still very, even though there's a big river flowing right through this, the New River, it's still very high elevation because the New River's got about 2,500 miles to go before it reaches the ocean. The James River's got maybe 250. And so it's flowing a lot faster than this is, and so it's able to erode this stuff much more quickly. So what's going to happen in the future? Well, this is a map showing the drainage divide between the Roanoke River, the James River, and the New River, with this yellow line, which is the West Virginia border, thrown in there just to confuse matters. But you can see, here's the Roanoke River. It's cutting its way up towards towards the New River Valley. This is a very steep slope. If you've driven up 81 up Christiansburg Mountain, what you're doing is you're climbing out of the Roanoke Valley into the New River Valley. And so the Roanoke River is now cutting upward into the New River drainage. It hasn't got there yet, but when it does, it's going to divert that drainage. That is, unless the James River gets there first, because there are several big tributaries of the James River that are also cutting back into the New River drainage. And if any of those get there first, it's going to divert that water into the James River drainage, and the James River will be the beneficiary of capturing all of the upstream water from the New River. Now, when will this happen? Nobody really knows. It's probably going to be tens of thousands, maybe hundreds of thousands of years. How is it going to happen? Again, nobody really knows. Some people speculate it might happen via a sinkhole that would develop in the New River Valley, and the water would just start flowing down the sinkhole and just pour out the side of Christiansburg Mountain, but nobody really knows. But sooner or later, this process is going to be repeated. The process happened first in the Shenandoah Valley and flattened it out. Now it's happening in the, in the Roanoke and the James River Valley. It's eroding quickly there, and it's going to happen here next. And so the Shenandoah Valley and the Great Valley of the Appalachians is basically slowly extending southward as these streams sequentially capture these older Mississippi Valley drainage streams. So again, this is all flattened out here. This is starting to flatten out a lot here, and you can see what's going to happen is these valleys are going to continue to lose elevation in here, and then once it happens here, this will start to lose elevation as well. And so that what will happen is we'll end up with a long, continuous valley going down through here. And the Blue Ridge south of Roanoke will now come to resemble the Blue Ridge north of Roanoke. It'll be a remnant drainage divide with a big water gap right there.